channels, regulations, channel selection, widths, frequencies, bands. Let us explore the invisible architecture of the airwaves, the complex and highly regulated world of wireless channels, frequencies, and bands. In our previous discussions, we looked at the physical frequencies of 2.4, 5, and 6 GHz. But knowing the address of the frequency is not enough. To manage a professional network, you must understand how that frequency is divided into channels, how different countries enforce strict regulations on those channels, and how a network administrator makes the critical decision of channel selection and width to maximize performance while avoiding the chaos of interference. The concept of the channel, defining the lane. To understand a wireless channel, imagine a massive highway representing the entire radio frequency spectrum. If every car on that highway drove wherever they wanted, there would be constant collisions. To prevent this, the highway is divided into strict, clearly marked lanes. In wireless networking, these lanes are our channels. A channel is a specific numbered subdivision of a frequency band. When you configure an access point, you aren't just turning on 5 GHz. You are selecting a specific channel, like channel 36 or channel 149. By assigning different access points to different channels, we allow multiple wireless conversations to happen simultaneously in the same room without them talking over each other. Global governance, the role of regulations. Because radio waves do not stop at property lines or national borders, they are considered a shared natural resource. Therefore, they are governed by strict regulations. In the United States, the FCC, or Federal Communications Commission, is the police officer of the airwaves. In other parts of the world, groups like ETSI in Europe perform the same role. These regulators decide 3 critical things: which frequencies are unlicensed for public use, how much power a router is allowed to transmit, and which channels must be shared with protected services like radar and satellites. One of the most important regulations you will encounter as a technician is DFS, or dynamic frequency selection. Many channels in the 5 GHz band are also used by military and weather radar. By law, if a Wi-Fi access point hears a radar pulse on its channel, it must immediately stop transmitting and move to a different channel to avoid interfering with the radar, if you're setting up a network near an airport or a coastal base. Managing these DFS channels becomes your primary administrative challenge. Channel selection and the 2.4 GHz congestion. Let us look closely at the 2.4 GHz band to see why channel selection is so difficult. This band is narrow, providing only about 80 MHz of total space, while there are technically 11 channels available in the United States. They are spaced very closely together. Each standard Wi-Fi channel is 20 MHz wide. However, the channels are only 5 MHz apart. This creates overlapping channels. If you put one access point on channel 1 and another on channel 2, their signals will bleed into each other like two people trying to have separate conversations while standing 6 inches apart. This is called adjacent channel interference, and it is the fastest way to ruin a wireless network. To avoid this, we follow the 1, 6, 11 rule. These are the only 3 channels in the 2.4 band that do not overlap. In a professional deployment, you will never use channel 2, 3, 4, or 5. You will carefully alternate between 1, 6, and 11 to ensure every access point has its own clear lane. The expansion, 5 and 6 GHz selection. The 5 GHz and 6 GHz bands solve the overlap problem by providing much more space and better spacing between channels. In the 5 GHz band, every channel is already spaced 20 MHz apart, meaning channel 36 and channel 40 do not overlap at all. This gives an administrator a much larger menu of channels to choose from, allowing for much denser deployments in crowded office buildings. The 6 GHz band, the frontier of Wi-Fi 6E and Wi-Fi 7, takes this even further. It offers nearly 60 separate 20 MHz channels. This massive amount of greenfield spectrum means that, for the first time in history, we can build massive wireless networks without having to worry about interference from our neighbors. The power of channel width, narrow versus wide. Now we must discuss the most important setting for speed, channel width. This is the decision of how many lanes we should combine together to form a single, high-speed superlane. This process is called channel bonding. In the standard configuration, a channel is 20 MHz wide. This is a narrow channel. It is very reliable and excellent at cutting through noise, but it has a limited top speed. If the environment is clear, we can bond two channels together to create a 40 MHz channel. This effectively doubles the speed. In the 5 GHz band, we frequently bond 4 channels to create an 80 MHz pipe, or even 8 channels for a 160 MHz pipe. However, as a network professional, you must be careful. Wider is not always better. Every time you double the width of the channel, you do two things. First, you increase the amount of background noise the radio picks up, which can actually make the connection less stable. Second, you use up more of the available spectrum. If you use one giant 160 MHz channel, you might not have enough room left for your other access points, causing them to interfere with each other. In a high-density office where hundreds of people are working, it is often better to use many narrower 40 MHz channels than a few wide 80 MHz ones. This ensures that everyone gets a reliable connection, rather than a few people getting extreme speed while everyone else struggles. The physics of frequency revisited. As we select these channels and widths, we must always keep the physics in mind. Low frequency, 2.4 GHz, long range, high penetration through walls, but very narrow channels and high interference. Best for IoT and basic coverage. High frequency, 5 and 6 GHz, short range, poor penetration through walls, but massive channel widths and ultra-high speeds. Best for video conferencing, high-speed data, and modern workstations. When you perform a wireless site survey, you are looking for the sweet spot where you have enough signal strength to support a wide channel, but enough physical separation to prevent your access points from interfering with each other. Administrative strategies, manual versus auto channel. One of the great debates in networking is whether to set channels manually or let the system decide. In a home environment, auto channel is usually fine. The router scans the air, sees what the neighbors are doing, and tries to pick the quietest spot. In a professional enterprise environment, we often use RRM, or Radio Resource Management. This is a centralized brain in the wireless controller that looks at every access point in the building. It creates a map of the interference and automatically assigns channels and power levels to every radio to ensure the entire building is balanced. However, in very difficult environments, like a warehouse full of metal racks or a hospital with lead-lined walls, a lead engineer will often perform a manual channel plan. This involves walking the floor with a spectrum analyzer and locking each access point to a specific channel to ensure absolute reliability for critical medical or industrial equipment. Troubleshooting the spectrum, interference, and noise floor. As a technician, you will often be called to fix slow Wi-Fi. To solve this, you must look at the noise floor and the signal-to-noise ratio, or SNR. The noise floor is the amount of background, static, in the air from other electronics. The signal is the strength of your actual Wi-Fi. If your signal is strong, but the noise floor is also high, perhaps because a nearby microwave is leaking or a neighbor is running a massive unshielded server, your computer will struggle to hear the data. This is why channel selection is so vital. If you find a channel with a lower noise floor, you increase the SNR, which allows the devices to use more complex modulation techniques like QAM to send more data in every radio pulse. A clean 20 MHz channel will often outperform a noisy, interference-heavy 80 MHz channel every single time. Summary of best practices. To manage a world-class wireless network, follow these 4 pillars of channel management. Strictly adhere to non-overlapping channels. Use only 1, 6, and 11 for 2.4 GHz. Match the width to the environment. Use narrow channels for reliability in crowded areas and wide channels only where you have a clear line of sight and high signal strength. Respect the regulators. Always pay attention to DFS warnings and ensure your country settings are correct to avoid interfering with critical radar systems. Monitor the noise. Use a spectrum analyzer to find the quiet spots in the air, rather than just looking at signal bars. By mastering the balance of frequency, regulation, and width, you will be prepared to build wireless infrastructures that are fast, stable, and ready for the future of the 6 GHz frontier.